Okay, these are actually my favorite type of circuit problems, and I really like switch problems with capacitors because it just throws back some nostalgia. Nostalgia of terrible times in physics too. Yeah, so I actually fucking hate this shit. Okay, let's analyze here. If the switch in A has been open for a long time, so we'll write t less than 0 means open, okay, and is closed at t equals 0. So at t equals 0, it's now closed. Okay, so, and this is for A, for part A. Yeah, I literally recommend writing this stuff out like how I'm about to do, like how I'm doing right now. Okay, now for part 2, or part B, suppose that the switch in B has been closed for a long time. So t less than 0, it's been closed. And then at t equals 0, it's opened. So it's the opposite. And this is part B. Okay, and then let's write down some information here, some conceptual ideas. Okay, so VC, well, they're calling it VO, but VC for the voltage across the capacitor. They're calling it VO, it's VC, same thing, right? So the voltage across the capacitor is equal to, okay, I'll write it like this. So meaning just right after, like right after you closed it, and VC 0 minus, which is right before you closed it, they're the same. So remember, the voltage in a capacitor doesn't change instantly, even if the switch is. The current can change, but the voltage across this capacitor can't change instantly. And if you're confused about this notation, think about it like in Calc 1 where you had the limit, right? How you talked about something tending from one direction to the other. That's what it means here. So that's our idea. We're going to use that information to answer most of our questions. And then let's maybe write out a formula. Here we go. VC of t is equal to what? It's equal to V of infinity plus V of 0 minus V of infinity e to the negative t over tau. Okay, so this is the formula we're going to use to find both of these answers. Okay, so let's start answering. Okay, I'll try to keep most of part A in black. Okay. So let's find, what do we want to find? We want to find VC. I'll go with VO now, okay? We want to find VO of 0, right? So, we want to find one of these, and these are the same thing, so we can just say it's VO 0. So we could draw the circuit as a 12 volt plus and minus. It's 2, and it was open before. Okay, so then it's just like this. 4 ohms, but nothing ever connects. And then there's this part over here that is, let me draw this better. 4 ohms, 3 farads. So this is the part we're focusing on right here. And this part, we don't, literally, it's not even connected. I mean, there's nothing happening here, right? Okay. And you ask yourself, well, VO, what is VO? I mean, I don't see a source. Do you see a source? I don't see anything. I mean, VO is just 0. Okay. That's it. Yeah, that's nice. And, okay, now the next part is the harder part, where we gotta find VO of infinity. Okay, now we draw the same circuit, except the switch is closed. Okay. This is going to be 2, closed, 4, and there's going to be 3. Now, DC conditions, right? This will be DC conditions when it's closed. So this will become an open circuit because capacitors and DC conditions act like open circuits, right? That's right, VO. Plus or minus here. Okay, so first we need to think about what VO actually sees in terms of resistance. So we'll say we want R, right? We want to see what resistance does VO see. Okay, well, it sees that there's a 2 ohm and there's a 4 ohm. Like that. That's what it sees. Okay, so if it sees that, okay, these two are sharing a node and they're sharing a node here. Yeah, I mean, aren't they in parallel? Yeah, they are. Right. So it's going to be 2 parallel 4, which is equal to 2 times 4 divided by 2 plus 4, which is equal to 8 over 6, which is 4 over 3. Okay. And then we could say that tau is equal to what? Tau is RC. So tau is, what's R? R is 4/3 and C is 3. So it's 4 over 3 times 3. As you can see, they cancel, so tau is just equal to 4. Okay. There should, yeah, thank you. Updated now. Okay, and now we think about what V of infinity is. So V of infinity, the voltage here, what is it over an infinite amount of time? Okay, so current comes out of here. None of it goes to here because this is open, right? None of the current can go to here because it's open. Like, why would it go to somewhere where it can't go anyway? So it's really just, there's a circuit like this, right? This is what's happening. There's a circuit just going like this. Voltage, current comes in and goes in this loop just like that. Now, just because there's no current right here doesn't mean there's no voltage, right? So, and this is in parallel with this, right? So would you say that they kind of share the same nodal voltage, right? Like the voltage right here has to be the same as the voltage right here, right? And that's just the whole concept of something being parallel. So VO is also VO right here. Very important. So you're right, plus or minus. Yeah. And then we could use voltage division. Voltage division. And we see that it's going to be what? Well, VO is equal to 12 volts, which is the source. And then we care about this one, so it's going to be 4. And then this will be the sum of this one and this one. And this is just the voltage divider formula. So this is going to be what? 12 divided by 4 divided by 6. Well, 4 divided by 6 is 2/3. And then 12, well, 12 times 2 is 24. 24 divided by 3 is 8. Okay. And this is what? VO of infinity. Okay, so that's very important. So now we can write V of t, and we could write this equation. So it's going to be 8 plus 0 minus 8 e to the negative t over 4. And if you want to write it nice and fancy, yep, I did my, yeah, if you want to write it nice and fancy, so you could write it like this: 8 1 minus, right, 1 minus e to the negative t over 4. Right, if you factor out the 8, this will be minus e, right? And then this will just be 1. So this is the answer. All of that. Okay. Let's solve for part B now. This information tells us what we're going to do. Okay, so if we drew the circuit initially when it was before we touched the switch, so before we touched the switch, this was a closed circuit. It was 12 volts, plus or minus 2 ohm closed, a 4 ohm connected, and we had VO here. And yeah, so this circuit right here is this same circuit. And then what did we say VO was? Well, we said VO was 8, right? Okay. So in this case, I mean, this is like two different questions, but in this case, infinity related to 8. And in this case, our V of 0 is going to equal to 8. So it's just, and that's just the concept of this was either, I mean, just look at it. These problems are kind of like equal opposites, right? That's how we can think about this. It's kind of like equal opposites here. So V0 of 0 is equal to 8. Okay, that's all nice. Okay, what happens if it opens? So if it opens, we draw the circuit again. 12 volts plus or minus 2, 4, and remember, there's nothing goes. This is open right here. This is open. I have to leave it open. VO plus or minus. And okay, you can see that obviously again, right? Same thing gonna happen here. Well, in this case, we call it V of infinity. It's gonna be 0, right? If you just focus on this part, so literally disregard that part because it's open anyway, so it doesn't even matter. Right here, I mean, this is going to be 0, right? I mean, this is just KCL. I mean, KVL, right? It tells you it's 0. Okay, so that's useful, but we kind of want to know the resistance, right? We kind of want to know what this what this sees at this point, right? Okay, well, if this is VO, the only resistance it sees is 4. Okay, the only resistance it sees is 4. Okay, then we could say that tau, RC, is equal to what? Okay, C is still the same, it's still 3. Let me write this in correct order. 4 is 4, and C is 3. Tau is 12. Okay, so then if we write our equation, same equation, so V of 0 of t, it's going to be, okay, infinities are 0, so it's going to be 0 plus, and then V of 0 is 8. So minus 0 e to the negative tau over 12. And if you want to write it nicer, we can write it like this. E 8 negative t 12. So they're kind of similar equations, but they're actually different, right? Because one describes the voltage that would go on if this was closed, and one describes the voltage that would go on if this was open. Right? So these are your two answers right here. Consider subscribing and liking if you found this video interesting or helpful. Leave a comment. Just leave any comment, just so I could, get this video pushed up in the algorithm.